Motion planning and obstacle avoidance is a key challenge in robotics applications. While previous work succeeds to provide excellent solutions for known environments, sensor-based motion planning in new and dynamic environments remains difficult. In this work, we address sensor-based motion planning from a learning perspective. To that end, we proposed a new representation based on point clouds. Given a robot start configuration, in red, a goal configuration, in green, and a set of obstacles, in blue. The motion planning objective is to find a trajectory that allows the robot to move from the start to the goal configuration while avoiding the obstacles. At each time step, the robot, considered as an embodied agent, senses surrounding obstacles with a panoramic camera. The point cloud built from the sensed visible surfaces of obstacles and expressed in the robot local coordinate frame, is then processed with a PointNet architecture to encode the obstacles. Then, the goal configuration vector is expressed in the robot local coordinate frame and concatenated to the PointNet obstacle encoding. This vector is processed by a MLP that generates actions, bringing the robot closer to the goal while avoiding obstacles. This method provides a way to learn a policy that allows to perform path planning while executing the plan step by step in an online manner. The method is based on the soft actor-critic reinforcement learning algorithm to train both the Q value and the policy network jointly with the encoding of the obstacles in an end-to-end fashion. In this part of the video, we show how our proposed approach compares to two state-of-the-art motion planning approaches. 3D synthetic environment. A 3 degrees of freedom robot is asked to reach a goal while avoiding obstacles. On the left, we observe how our approach performs path planning and executes the plan in an online manner to reach the goal. Our method only needs to explore 13 nodes to reach the goal. On the right, the state-of-the-art INRIA 2019 method runs neural planning from both start and goal configuration to find a path. Then, lazy vertex contraction to shorten the found path, and next, feasibility checking to detect part of the path that are under collision. Finally, it runs iteratively neural replanning in a coarse level to connect the nodes where there is a collision on between them. Once a path is found, the robot can use the plan to move along it and reach the goal. This method explores 300 nodes to find a solution. Slot environment. In this environment, a 6 degrees of freedom robot has to reach a goal configuration passing through a slot of a specific size. For this task, we compare the performance of the classical planning algorithm by RRT to our approach. Our method runs online by computing and executing step by step the solution to reach the goal configuration. It finds a solution exploring only 18 nodes. BiRRT expands nodes from both the start and goal robot configuration until it finds a possible solution. Once a solution has been found, a direct connection between pairs of robots' configurations along the path are checked to shorten the path. Finally, the planned path is executed by the robot. The method explores 15,607 nodes to find a solution. One of the advantages of the proposed approach is its capability to generalize to unseen environments. We show next how our method behaves in different environments. Training, 3D, boxes environment. During training, the agent interacts with environment instance composed of 3 to 10 static boxes generated with random sizes, positions and orientations. Due to these interactions, the agent learns to do motion planning in instances of the 3D boxes environment beyond the ones seen during training. Besides, as we show next, the learn policy is able to generalize to new kind of environments. Generalization, 3D, YCB. The learn policy generalizes well to 3D YCB environment. This environment is composed of real objects from the YCB dataset recorded with RGBD camera. Failure cases. Sometimes, the policy fails to generalize and to find an optimal path. Here, we can see how the agent gets stuck. Generalization, 3D, dynamic. Additionally, due to the online nature of this approach, the learn policy is able to cope with dynamic environments. Summing up, this work introduces a new framework for neural motion planning. Obstacles are represented by point clouds and encoded by a PointNet architecture. PointNet encoding and motion policy are trained jointly with reinforcement learning. In future work, we will extend this approach to robot with multiple links such as robotic arms.